Good morning, at least when I'm recording this video. This is my first time attempting to give a video presentation, so I hope you find it useful and informative. Certainly for this conference, my title, the U.S. Materials Genome Initiative and the Materials Data Infrastructure, is very symmetric with the title of the conference, and so I expect to find a great deal of interest in the other talks that we'll see today, and I hope you find this one useful as well. So briefly, I'm going to describe the MGI in the US and the National Institute of Standards and Technology's role in supporting that initiative. I'm going to talk about the data infrastructure, what its current status is, which clearly is that we have elements of it, but there's a lot more to do. And then I'll talk about an ideal we have, which is called the National Materials Data Network, and perhaps the international scope that will eventually occur. And how we can meet the needs and what the human factors are, the social factors that are perhaps blocking our path to success. Finally, I'll talk about where the initiative stands in 2020. And if there is time, I will also talk about AI, artificial intelligence, and how that is driving some transformations that we're seeing. So let's begin. I usually start with a joke, and this is the one I start with. It doesn't really quite work as well over video, so I decided to include a different joke, which is really talking about incentives, which I'm going to talk a fair bit about in this talk, and how people behave depending on whether or not there are carrots and or sticks driving their behavior, and how that changes their incentives. So first, I will talk about the MGI, which is an initiative, and that's a fairly simple idea, which is a statement by the president. In this case, the initiative was rolled out by President Obama in 2011, that the agencies of the federal government should work together to try to achieve a goal that is larger than the mission of any single agency, and that's all an initiative is. So you're probably familiar with the MGI, but there's also the National Nanotechnology Initiative, the BRAIN Initiative, and many, many other initiatives that span government and has a lot of agencies working together. So in this case, the Department of Energy, National Science Foundation, NIST, the Department of Defense, etc., are all working together to try and make the MGI happen. And we are now 3.5 years into a different administration, and the MGI is still going strong. So when the initiative was rolled out, its goal was simple. In this case, it was to decrease the time to market by half while keeping costs down for the discovery, design, development, and deployment of new materials into manufactured products. And to do that, we needed to create a materials innovation infrastructure. Now, if you look at that infrastructure, it's composed of experimental tools, computational tools, and digital data. These are really just the elements of science and engineering, so there's nothing particularly remarkable there. What is somewhat remarkable is the need to tightly integrate these so that we can accelerate this discovery, design, deployment of new materials. And if we do that, then we'll achieve national goals in energy security, human welfare, etc. And of course, this is an international conference, so one could ask the question, how does any particular country benefit from such infrastructure? Because these are hardly local to the United States. And of course, the answer there is the final point, which is equip the next generation materials workforce. And in that case, what really has to happen is that you need the people to use this infrastructure wherever it resides. And it's having that talent by cultivating it or bringing it on that you then can exercise the infrastructure and achieve the goals of the initiative. Of course, the initiative spans this enormous continuum from discovery of materials, deployment, all the way out to manufacturing. So to make this happen is a non-trivial task, and of course the MGI is working at all of these length scales, although some of them are more challenging than others. the G, the genome and MGI. Now, there are two groups of people that don't particularly care for the name Materials Genome Initiative, in my experience, and those are material scientists and biologists. And that's because the experts, of course, know that the name is not particularly precise, and scientists don't particularly care for imprecision. In this case, it's really more of a metaphor than anything else, and that sometimes we don't care for those. But nonetheless, it does serve a very valuable purpose in indicating that we are trying to work our way up from sort of basic building blocks of knowledge, in this case, like a genome, to design and discover new materials. So we sort of accept the initiative as a shorthand, the name as a shorthand for that. So in my mind, what is the genome, or what is the MGI? We have this idea here that there are data and models out there that we need to understand or incorporate into this loop that I have below on the diagram, which is a classic description of computational multiscale modeling. And so here you have that description, and you're moving from all the way up the line from quantum, nano, micro, macro. You're getting data, though, for that from both experiment and simulation. And the question you have to ask is, where did you get that from? How did you make that decision? All of that information is fed into this multiscale simulation to make predictions for targeted properties. And so you need to pick data, you need to pick models, and it's not trivial. No one can just start ab initio and work your way out to a car. So how do we do that? And so the idea behind the MGI really is to capture as much knowledge and information as we can that will then allow us to exercise this predictive loop and make the predictions that we need. And finally, of course, the M, the materials. That's why all of us got into this business. And the real question here is, why did the MGI happen when it did, now almost 10 years ago? And I would maintain, if you look, for example, at these two steels, of course, as materials people, we know that even for the same composition, depending on the the processing of the two materials, you get very different, in this case, microstructures, which then, of course, yields very different properties. So it's our ability to predict such structures that really starts to arise in the 2000s that allows us to then exercise all that loop again and make the predictions of materials like this. And so once it became apparent that we could really move from up this chain, I think the MGI becomes self-evident. So, of course, that very idea is not a new one, right? The ideas around multiscale modeling, around prediction of materials have been around forever, and they've made money, and they're very practical for real companies. So, for example, Apple announced in 2014 their new watch, and one of the things that was remarkable when they rolled it out was they also talked about the new materials that they had designed concurrently with the design of the watch, and could create, harder gold or, more scratch-resistant aluminum or whatever it was. And so the question we really have is, how do we, can others do this? And so there was a nice example from Kevin Anderson, who is at Brunswick Mercury Marine. They make, motors for boats, and they have all of this materials design programs, within their own shop. And I think, there's a long list here on this slide of activities that they're doing, so you can see how they're using MGI style approaches. Perhaps one of the most important things is number 7 here, which is that people who work in the company have goals that require MGI skills, and so the management teams in these companies actually understand that MGI is a good investment for them. And so it's building that into the culture that was very important for Brunswick Corp. So, we have done an economic study of what would happen if all of the companies in the US were to take on such types of practices, and the guess, while obviously somewhat uncertain because this is a model, suggests hundreds of billions of dollars in net benefits. And I should mention, anybody is welcome to these slides, and so I hope you can enjoy them because obviously I'm going rather quickly. So the question we have to ask then, if these ideas are in some sense basic, is, how do we get to the goal of the MGI, which is to really lower the barrier so that not just Apple Corp, not just Brunswick, but a smaller shop, a smaller number of engineers, perhaps one, perhaps two, can reach out into the infrastructure and do the materials design that they need, without needing to be a multi-billion-dollar revenue company. And this will, of course, benefit not only the small guys, but also the bigger companies, because then they can do more of it more cheaply, which benefits them. So the MGI in sum, right, is about improving our ability to design and deploy new materials, obviously faster. But to do that, we really need better data, better models. And if you think about it for a few minutes, you'll see that the MGI is really just a direct consequence of improvements in computational power and associated models, coupled with, of course, the disruptive consequences of the internet itself. Sharing data seems challenging at best before the existence of the internet and sort of trivial afterwards. And so then the questions become more technical. But of course, there are only a limited number of ways to get that knowledge, to get that data that's going to fuel this. And one of them is, of course, high throughput computation, which was a very early success in the MGI. And there, of course, you had better trust the models that are generating that data, or, of course, that's not very valuable. You can do high throughput experiments, try to generate as much data as possible. If you do that, once again, you may have to make trade-offs between the quality of the data versus the quantity. And in some sense, it would be very nice if you could somehow get it from everywhere. That is, there is an entire literature out there. You'd like to be able to mine that, and even more ideally, you'd like people to publish their data that supports those publications, but it needs to get published, and that means we really need to think about how we publish data, whether there are incentives to publish data, and of course, that is a large part of the discussion that's going to go on at this conference. So this is important to do. All right. So in 2013, not long after the initiative got rolling, we defined our role in support of the MGI. And to do that, we created this diagram, which I've already shared with you, so I won't go through it again. But the question we had was, what's our role? What can we do to support this? And we thought about it, and we said, well, NIST really is about the delivery of high-quality data to the world. And so how can we, within the frame of delivering data and exact science, improve on that? And of course, the first thing we said was, well, if people are interested in data, you need a place to put it. That's the first question you're going to have to answer. And so we said, well, there have to be repositories. So we set up one of the first public data repositories, the Materials Data Repository at NIST, and people can still use it to this day if they want to. But it's hardly the only thing. It's sort of just the minimal thing. So then we started to think about what our role would be within that context. And we realized that, of course, while NIST could set up data repositories, it was hardly going to be the only place, and we couldn't possibly be the only keeper of data. So we recognized that there must be a big federated system around the world of data repositories. And then we said, well, what are we going to do? And so the first thing we said was, well, we're NIST. We're going to make sure that the quality of the data is as high as possible. That's really our role. Get that extra decimal point on the best measurements and give people the tools so they can assess the quality of the information. We also knew that we would have to move the data around, that is, around publication and transfer of data between models, between repositories. And so this is this idea of enabling and enhancing the exchange of data. And we also knew that it would have to be driven, that if we had that infrastructure, this would drive us towards new methods, and new metrologies. And so we were thinking specifically of data-driven science, although we realized that good data-driven science was going to be well off in the future. And in a happy coincidence or happy occurrence, I don't know what to call it, we turned out to be wrong in the sense that it came very quickly. And so if you haven't seen the book, The Fourth Paradigm, I recommend it. Data-driven science is what it's about. It has very little actually about materials in there, but I think if it was written again today, materials would be front and center. So about 3 years ago, almost exactly now, the TMS put together a group of people to assess the existing materials data infrastructure and tried to answer the question of where the infrastructure needed to go and what was missing to make it happen. And I think it's a really good study. I recommend people pick it up. You can download it for free from the TMS website and take a look. I'm not going to go through the whole study here, but I just thought that this was a particularly interesting approach that they used, where they took a look at all the possible recommendations they could make about the infrastructure and tried to define, what were the high risk, probability for success, impact quadrants, if you will. And so if you have a very high impact and very high probability for success, you probably want to do that, for example. And then there may be some stuff that is very hard to do and perhaps not so useful or very difficult to achieve. And so maybe you want to wait on that. And so, they then put together a shorter list, and this is not the full list, of where things, of recommendations that they made. And so I've listed them here because I want to talk about whether or not in the 3 years since those recommendations were made, we've made progress. And so number one was strengthen the materials data infrastructure core and repository registry and tool development. And I would claim we've done a very nice job there. Obviously, there's way more to do, but we're making great progress. Sustain and grow the materials data infrastructure dedicated funding programs. We're doing pretty well there. I wouldn't say they're growing as fast as we'd like, but real progress. And clearly in Europe, you're making real progress with the Fair DI movement, so that's very exciting. Now, recommendation 3, create, execute, and monitor incentive mechanisms. I think this is where we have come up significantly short, and I'm going to talk about ways we can start to address that. I think we could do much better. Okay. So what is stopping us? So how do we get to MGI 2.0, MGI 2020? I would claim, as I said, incentive failures are at the heart of this. There are a number of reasons that people aren't moving forward. Some of them are around ignorance. I'll talk about that very briefly. Technical issues and professional, which I think is the most important. So ignorance. In some sense, this is the easiest to solve. If you don't know there's a data infrastructure, you don't know it's there for you, you can't do anything. So you hopefully see a talk by me or one of my colleagues or a lot of the very bright people that are working in this space, and then so problem solved, easy. Technical issues. So the question there now is, well, what kinds of tools do we need? What kinds are being built? So a small digression here while I talk about what NIST has been doing to solve some of the technical issues. So we looked at the astronomy community, which has been enormously successful in this space for decades. So this is the Virtual Observatory, the VAO. They have a website. You can just go there, and essentially all of the telescope's data in the world goes into the Virtual Observatory. And there you get a real value multiplier because, for example, Hubble data from the Hubble Space Telescope, 2/3 of the publications based on that data were research that was done by people who did not take the data. That is, you're getting about 3 times as much research as you would have if only the PIs were able to do the work. So you could say, well, astronomy, that's very nice. You can get all the data. In some sense, it's much easier than materials. All they need to know is the position in the sky and essentially the light frequency for the various types of measurements. and they can sort of standardize that data pretty straightforward. For materials, the problem is we have measurement types, of course, but we have all this processing history, so it's much more complicated. And kudos to Zach Trott for pulling this slide together. So this one looks way harder, and some people would throw their hands up in the air and say this is impossible, but it's not. It's just much worse. And so pick a square, get to work. That's been sort of our attitude, and we have been trying to solve the problems in some of these subspaces for a number of years. So a question might be is where to start. What is the telescope in this case? And I think it's fairly clear that one of the major places we should be making investments is beamlines. This happens to be taken from the Diamond light source in the UK, and it's just showing the growth in data, and it's looking suspiciously exponential, and of course that geometric type growth suggests Moore's law, which isn't surprising because the detectors themselves have been scaling associated with these kinds of infrastructures. So we should be looking at the beamlines to help drive us with our data infrastructure. NIST itself has put together something we call the Materials Data Curation System, and that's a subset of something we call just the Configurable Data Curation System, which actually has recently been used to curate data around the COVID-19 pandemic. So these tools are very flexible, but nonetheless very useful for trying to describe materials systems. So you could get that for free off GitHub, and you'll certainly ask me questions if you want later. There are lots of infrastructures out there, and this is just a bunch of pictures that I grabbed from the web, including this new Optimade, which I think is very exciting because it's an attempt to try to unify and make a single interface to all of the quantum computational databases that really were some of the drivers for the MGI. But there are things all over the world, and hopefully I've captured some of your favorites here, but there's lots more infrastructure that we need to create. So I was talking about professional impediments to the use of the infrastructure, and of course, that's where I think the main challenge now lies. And so I like to use the example of Galileo to illustrate this point. Galileo was extremely famous for discovering the moons of Jupiter, showed that physical law applied to a different heavenly body, and so, had a good reputation in that sense. And he then pointed his telescope at Saturn and thought he had seen moons, as the upper right picture shows. And so he didn't want his competition to find out about that, so he decided to publish. And he did that as a 37-character anagram, which essentially said, I found the moons of Saturn, but didn't tell his colleagues, and so they would have to decode the anagram, and he was the only one that could do it. So he then could keep priority on it if somebody else did it, but he didn't want to tip off his competition. Now, I believe that all academics would behave this way if they were allowed to. And so we've put in place systems that say basically that's not okay, right? That if you want to publish, you publish, and then your peers review it, etc. And that system's evolved over centuries and has a lot of good properties to it, but obviously we could do better. So the question we have to ask is, what does it take? Well, in the case of Galileo, right, basically the funders of science, the patrons at that time, said, well, you shouldn't do that. And then academia essentially adapted to a publishing environment and built metrics around that. And now there's a sort of economics of tenure which says you have to publish, et cetera, publish or perish. So to do the same with data, we really need to change the rules again, but we also need to give people the tools so that they can publish data, and that's a lot of the technical issues I was talking about. But it's more than that. So let's address the real issue. Oh yes, I put in this FAIR statement. Of course, the tools and the rules really get at this notion of FAIR and culture change. And so it's very exciting to see the FAIR movement really starting to gain traction. I think it's going to be a very useful vehicle for MGI and for all of the parallel efforts around the world. So, the real issue. Until people can do science and engineering on platforms that nominally hold data and models, the infrastructure really isn't going to happen. And so what do I mean by this? Well, if I told you that you could go to one of these websites, you put your data there, you can now combine that data with other data, you can build off the prior work of your colleagues, discover interrelationships in that information, and perhaps you can run a machine learning model or some more classical partial differential equation, physical model on that information. Well, that's a very useful thing that would allow you to actually write a paper and publish it. Then the fact that you've put your data onto this platform is just a side effect to you. You didn't put it there for that. You did it there for the science or the engineering goal that you had. And to me, once that happens, almost all of the barriers go away. So we need to get these sites, these platforms, these tools to a place where people want to put their data there because they have a different goal other than just publishing the data. They want to put their data there so they can do science, so they can do engineering. So how do we get there? Right, so as I said, fame and fortune. Of course, the other reason people would want these kinds of platforms is to make money, particularly if you're talking to a company. And so the motivation may be slightly different for academia in industry, but nonetheless, you have the same sort of practical goal in some sense. So to make this happen, in my mind, we need to create what I call the National Materials Data Network. Of course, this could be international, depending on how we all want to play together. And I'm very excited by that idea, so I'm happy to further those discussions. So this really is a social idea almost more than anything else, which is that we need to have an ongoing conversation that's in some sense formalized and may even have some kind of governance that allows us to identify all of the gaps and what it needs to get the platforms to the place. So this needs to be broad, academia, industry, and government coming together to divide the development of infrastructures. And once we have defined, a roadmap, whatever you want to call it, that community can then come to funding agencies and articulate those demands. And then the funding agencies can say, aha, this is what is needed. The community understands that this is the way forward. So this must be the set of priorities we should pursue. I've seen some promising trends in the US on this. Recently, the community created something called the Materials Research Data Council. It's in its sort of infancy. I think they stood this website up in January. And it certainly looks like an attempt to model something like a national materials data network. So I'm pretty excited about this development. We'll see what happens. So finally, the MGI has been around for a while. Our last strategic plan came out in 2014. It certainly was time for us to have another strategic plan that reflects the accomplishments that have been made and where we're going. And so the plan is hopefully coming out sometime this summer. And it has three title goals, which are that we should deploy the materials innovation infrastructure, harness the power of materials data, and educate and train and connect the materials R&D workforce. So as you can see, this fits very nicely with the purposes and goals of this conference. And so I would hope the MGI will continue to drive international interactions on fair data, materials genomics into the future. And so I want to finish with one more comment, which is around AI and machine learning, which is that it is a true driver for what's going on with the MGI. It's been very exciting to see all of the machine learning and AI activities within material science. And because, of course, the food, if you will, for all of these AI machine learning models is large amounts of data as much as possible. This has now changed the conversation that we have to have, because I think it's made it much easier for us to argue that if you want AI-ready data, then we need these infrastructures to make that happen. And so I'm very excited about this advent. So I will just also mention that the advent of autonomous AI-driven material science infrastructures has, in some sense, substantially altered the way I am now thinking about how one does materials science, because these kinds of closed loop systems are going to be profound. So with that, I hope you have enjoyed the presentation. I look forward to the Q&A when we do this in real time in early June, and I thank you very much for your attention.